Most of you probably listen to music and you change the equalizer setting on your phone or your car or whatever listening device you're listening this video or like music towards. And have you ever wondered what would be a similar concept to change these equalizer settings or like tweak how the image would look? Can we do something similar we do with audio? Let's demystify and decipher the world of frequency filtering through Fourier transforms in today's video. Let's imagine we want to build an image up from some mathematical function. One simple way is we save all the pixel intensity values like we have done in the past, and for a color image we do like 3 channels of them for each pixel, and we save this and we say, hey, like this is what is the mathematical number system which represents my image, right? But in today's video we will talk about different ways to represent the image. Maybe this will help us compress the image into something smaller, which means that to save like 100 by 100 pixel image, instead of having 10,000 values or 30,000 values in terms of color, can we do that with much lesser quantity, right? Can we learn the essence of what the image looks like through a mathematical function or through some mathematical magic is what we are going to look at today. So first, let's meet our friend Lena. Lena is one of the most important images in the field of computer vision or image processing. This was the image which was digitized from the magazine Playboy. And like this image is great because it has a face, front, right and center, has a bunch of features which are like different amount of variations, and it has like objects with different angles and orientations, and we will see why that is important in today's video. Let's first think about how we can take this image and break this down into some quotes known components. The answer could be we have some known set of features. The known set of features could be what a hat looks like, what a feather on the cap looks like, how the eyes are, how the nose is, and how the hair is, and how the back bed frame is, and so on, right? What if we want to take the same ideology and use the same thing for a completely different image, right? In this motorcycle image, it's in an outdoor scene and has very little resemblance to what is the indoor scene on the Lena image on the left, right? If we start crafting handcrafted features or known components for each and every single scenario, we would be left with a lot of variations which would be really hard to work with, and it would be really painful to do this forever, right? And what if you wanted to do this for all the images? Which means that we have all the images under the roof of the sun. It could be any scenario from indoor to outdoor. It could be like a living object, an inanimate object. It could be any single thing that can happen, right? Images come in various forms, and like of course taking images with different cameras, different settings, change all this stuff, right? Can we come up with some known feature structure which we can use to basically extract from all images, right? The question is, what features would those be, right? So that's what we are going to delve into today, and we will come up with a beautiful mathematical formulation which is pivotal to understanding the feature space in images. Before that, let's go into the world of math and let's say a magic trick. As with all examples in computer vision or image processing you have seen in the past, we are going to basically make the image from color to grayscale. To make life easy for us to discuss, remember that everything we talk about the grayscale image can be applied to a color image. You just have to do this multiple times for each channel. Okay, so to make life even simpler, let's look at one single row of this Lena image, right? And this is what it looks like. And if I take this structure of Lena image and plot this out as intensity value on the vertical axis, and like the spatial dimension going from left to right, like different columns in that specific row, this is what it would look like. Okay, now let's call this function x of t, where t is the time Here the time axis is basically the spatial dimension going left to right. And what we want to essentially do is this x of t is a pretty complicated function, right? If you look at it, it has a bunch of peaks, it has a bunch of valleys. It might be really hard for us to write a mathematical equation for this. Remember that we are doing this for any image in the world, right? For any image in the world, this function could be arbitrarily complex, and it's hard for us to write a simple equation which determines, hey, this is what x of t looks like. So instead, what we will do is we will break this function f of x of t into something simpler, which we can actually model and utilize to make our life easy, right? So in other words, if you want to write this in math, we want to write this function f of x of t as some summation of f of t, g of t, h of t, and up to like k of t. Again, remember that these functions f, g, h, and k are what we have to determine what they are. And in some sense, we will basically craft these functions in a way that it is simple for us to make use of it so that we can build up to this x of t, right? And we essentially want to establish some link between all these functions on the right hand side, right? So let's pick a simple function for f. It could be anything, but since we know a lot of these things from physics, a lot of things in the nature or in the world can be modeled through a sinusoidal or a cosine function, right? So let's pick f of t as a sine of omega t. Again, remember that omega here is just an arbitrary parameter which we are going to change the frequency of the sine wave, right? How fast this sine wave oscillates up and down between -1 to 1. That's what we are controlling with this omega, right? Also remember that we can multiply this sine of t with some amplitude a, which will let us basically scale this up and down, and we can also add some number to shift it up and down as well if we need to. Great. So, and if we add like some phase shift to omega t, like we do omega t plus phi, we can shift the sine wave left and right as well. Great. So let's take this function f of t and let's break this down into a bunch of functions like we discussed before with different values for omega, right? As you go from bottom to top, we are basically dividing the omega by 2, or it's halving every time you go from bottom to top, right? The question is, to represent this yellow function, we can represent it as a summation of all of these guys, and it would essentially give us back the yellow color waveform. The question now is, if you have something like a square waveform, how many sine waves would we need to represent something like this, right? This is what we would call as the ideal contrast or maximum contrast, which is going from white to black to white to black. And again, this is one row of the image, right? I want you to take a second and think what the image actually would look like here. The image would look like basically alternating white and black stripes with like it being perfectly divided from white to black. Okay, and there is no gray value here. Great. So to answer the question, how many sine waves we need? The way we can think about it is in the top 4 circles, we basically have the different sinusoids. Again, the circle diameter basically shows us what's the frequency of that. And in the bottom, we are basically superimposing all of these circles, right? At the end of the day, we want basically the cyan circle, and then we add the green circle on top of the tip of that, and then the red circle on the tip of the green circle, and then the pink circle on top of the tip of the red circle. And that's what is going to trace out the final shape or the final waveform, which we were just talking about. So let's play this. You would see that we essentially obtain a waveform which is sort of similar to what we saw before. The waveform is called a square waveform, what we saw before. But what we see here is not a perfect square waveform. We see that there's a little bit of noise. The axis, when it goes from like high value to low value, is not perfectly vertical. And even at those high or low values, it's oscillating ever so slightly, right? This is sort of like noise. But depending on like how many of these waves we have, the approximation can get better and better, right? So the question is, how do you know how many sine waves would you need for an arbitrary representation of a function, right? It's really hard question to answer. So let's go with the simplest answer. The simplest answer is, given infinite number of sine waves, we can basically approximate any function, because like you can basically fit every single frequency under the roof of the sun, right? That's the best part here. This comes from the fact that any function can be approximated with a high enough degree polynomial. You can think about taking each sinusoidal wave and stretching it out in a way that it represents a small piece of the function, right? And this is a beautiful theorem in math. And if you have ever taken a calculus class, you have definitely heard about this. This theorem is called the Taylor series expansion or the Maclaurin series of expansion. Right? I'm just showing you the math here. There's a video which will come up later on in the series, which is going to explain this in more detail, because this is a very fundamental concept. But for now, let's assume that you know what Taylor series and Maclaurin series is, and we move forward. To give you just like a quick 10-second gist of what this is, as we have our waveform in black here, which is the sine waveform, we start approximating this with different order polynomials, right? Red is basically the order 1 polynomial. Then we have something like the orange one, then the yellow one, then the green one, then the blue one, and then the pink one, right? With increasing order of polynomials, you're increasing the domain where this fits the function pretty well, right? Again, remember that sine wave is a pretty complicated model because you actually need infinite of these polynomial values to actually model that. But if it's something simpler than that, it would be much easier, as we saw before. Great. So this brings us to one of the most influential theorems in the field of signal processing, computer vision, and image processing. This is called the Fourier Transform. So let's hail to almighty Jean-Baptiste Joseph Fourier. In 1807, Fourier basically said that any univariate function can be rewritten as a weighted sum of sines and cosines of different frequencies, which we just saw intuitively before. This is what Fourier said in 1807. When he came up with this formulation, nobody believed in this. Even the big people and big guns like Lagrange, Laplace, Poisson, and other big people in the field of math did not agree to this ideology that, hey, like any function can be represented as a sum of cosines and sines, right? And as a matter of fact, it wasn't even translated into English until 1878. So almost like 70 years we were kept away from this hidden gem. So a slightly modified formulation of what Fourier wrote in 1807 is called the Fourier Transform, right? And we will look at the Fourier Transform in a second. The Fourier Transform is represented by the script f, and a Fourier Transform is given in the continuous domain as this function where we are integrating the function f of x with this e power quantity, which is like the Euler style thing. And the idea is that you're taking something from the spatial domain on the right hand side, which is f of x. Remember that we had our row wherein like we were moving from left to right, and that's f of x. And f of u is something which gives us a representation in something called the Fourier domain, right? And we will talk about what that is in a second. And in the discrete version, we take the same thing, we discretize the entire thing, and we basically replace integration with summation. As you would clearly see, the Fourier domain has real and imaginary parts. In special cases, it can only have real components. In special cases, it can have only imaginary components. But in generality, it has both real and complex domains, right? So we went from a single channel image for a grayscale thing to double channels in the Fourier domain because we have real number part and the complex number part. Essentially, we took you from the spatial domain or space to the frequency domain in this particular case. Of course, no transformation is complete if it doesn't have an inverse, because it's not much utilitarian if we cannot like reconstruct the original thing back, right? So we have the inverse Fourier transform denoted by f inverse, the script f inverse here, and essentially you can think of it as like swapping the little f and the capital F on the left and the right, and changing the negative in the e power to the positive, and this is the continuous domain, right? Remember that in the previous case we were integrating over the spatial domain. In this case we are integrating over the Fourier domain or the frequency domain. So the discrete version of the signal is going to be similar. Again, replace the integration with the summation, and then discretize the signal on the exponent. This formulation takes you from frequency to space. So the one sentence version of what a Fourier transform gives you is that it's essentially helping you count how many of certain frequencies are present. Frequency here is represented as if the rho was a sine wave, basically like the values of the intensity going up and down as a sine wave. How many of those sine waves would you need to represent that particular row, right? Remember, we are splitting each row, which is an arbitrary function x of t, into a bunch of sum of sines and cosines. And the idea is that we are trying to look for what is the frequency of these sine waves and what is the frequency of these cosine waves to get the original reconstruction of x of t back. We are decomposing this x of t into various sines and cosines. The equivalent of this is in audio. When we boost the bass signal, we are boosting the values of the lower frequency components to get the thumping noise. If we are boosting the treble, we are boosting the frequency at the higher spectrum where the tweeters go more amplitude, and we are trying to essentially do something like that in the image domain here. And in the image domain, the only thing we have is the intensity values. So we are messing around with the intensities to see in a way how we can essentially break the image up into some version of beats, if you want to think about it. This is essentially visualizing each image as some audio-like waveform, and we are basically able to reconstruct the image from an audio-like waveform, and that's what we are trying to do here. And the intuition will become more clear as we see a few more images in the next few minutes. Now let's look at some of the properties of the Fourier transform because it's super useful. The Fourier transform has linearity property, which means that if you have a scaled version of the Fourier transform in the spatial domain and then you add two of these things up, you can go into the frequency domain and you can add up the Fourier transformed versions with the same scaling as well. Okay? If you scale something in the spatial domain, it's essentially going to be scaled in the Fourier domain in almost like a quote-unquote inverse way. Shifting in the spatial domain, moving the signal left to right, basically will be a shift as a scale in frequency as shown here. And differentiation is going to turn up something like this. One of the most important Fourier transform theorems is called the convolution theorem, which means that if you take an image and you take another filter, you apply convolution between them, which is like filtering that image with that filter. Essentially, you can take the Fourier domain of the image and the Fourier domain of the filter and element-wise multiply them. This is amazing because we went from a very complicated thing like convolution to something very simple like element-wise multiplication. Right? And this is one of the most important theorems which is used in the field of computer vision and image processing to make things really, really, really fast, right? And it's amazing. So one of the major things about the Fourier transform is that if you just implement a standard version of the Fourier transform, it is pretty slow. It's extremely power hungry and extremely computationally heavy to implement it. One of the biggest discoveries in the field of algorithms for Fourier transform was something called the fast Fourier transform. This specific variant is called the Cooley-Tukey FFT algorithm, which basically makes the O of n square Fourier transform, where n is the number of pixels, into O of n log n. This can save us exponential orders of magnitude just by utilizing a concept like this. So at the underlying principle, it uses something called the butterfly diagram, wherein it uses like a binary search like method to split the operations in like a in a way that like it reduces your computational complexity by a significant amount, right? I will have another video on how this looks like because this is such an amazing concept. It deserves its own big video. But for now, you can read up on it. It's a self-read. It's called the Cooley-Tukey FFT algorithm. Right? If you have a million pixel image, which is not that big deal in today's day and era, right? You would have 16.6 million operations versus 1 trillion operations if you implemented the standard discrete Fourier transform as we saw in the previous slide. Great. Now let's take a understanding of how the Fourier transform looks like through visuals, right? So let's imagine you have an image which looks like this on the left image, right? And to make life simple, I'm going to tell you that the function of each row is a sinusoidal waveform, right? It's a sinusoidal waveform which starts at negative, like 0, and then goes to negative, and then goes up, and so on and so forth, right? Remember the example we started with, the square waveform. The square waveform is basically not smooth version of this, right? It's basically black, white, and so on. But this is a nice little gradation from black to white, right? And in this particular case, the -1 is going to be mapped to black, and the +1 is going to be mapped to 255, and the 0 value is going to be mapped to 127. Great. So now let's take the Fourier transform of this image and let's see how it looks like. So we start with a 2-dimensional matrix, which is the same size as the original input image, and we want to start populating this, right? As you go from the center is the origin, the frequency increases. Remember that there is technically nothing called the negative frequency, but for mathematical sake, because when we implement this, you basically get a symmetric waveform on the left and the right hand side. So we basically will compute it for one chunk, and then we will copy paste it in some sense for the other 3 quadrants. Great. And as you go up from the bottom, that is basically the angle or phase of the waveform. So remember that we have a sine waveform with some frequency, and let's assume that the angle is 0. So I want you to pause the video, take a second, think about what would appear on the screen. Just a hint that it would be the same thing on the left half of the Fourier transform image and the right half of the Fourier transform image. But how many values would we actually see here? If you were thinking just one, you were absolutely correct, because remember that we have one sinusoidal waveform in the entire image. That means that it's going to only have value at one single frequency, which is the equal to that of the sine waveform, right? And remember that I told you that it's symmetric left and right. Again, it's more of a mathematical representation, and like in image processing, the negative frequency does not really have much physical significance, right? It's more of a mathematical thing. So you will have basically one dot on the right hand side, and because of the virtue of symmetry, you'll have the same dot on the left hand side. Great. So now let's change the frequency of the sine waveform. I'm going to play this one more time. So what do you think will happen to the 2 dots? Remember that as you go away from the center, the frequency increases. In this particular case, we increase the frequency almost doubled. So the dots are going to move outwards, right? And that's what just happened. Great. So let's go back to the original image, and let's now tilt the image in a way that it's not exactly vertical. Now it's at an angle, let's say like 30 degrees or something like that, right? I want you to take a second and think what would happen. Remember that the horizontal axis is frequency, and the vertical axis is essentially our angle or phase. So if you were imagining that you would have values diagonally, you are absolutely correct. And you would have values diagonally because you have one value for the angle and the phase, which is non-zero, and you would have a reflection point of that on the opposite side, right? I want you to pause the video for a second and think, why are these not exactly 2 dots? Why is it like a star-like pattern? So welcome back. Now that you've thought about it, what happens is when you actually take an image and represent it in actual pixels, which means that you're discretizing the real continuous function, which is a sinusoidal waveform at an angle, you basically do some amount of interpolation, which we will talk in one of the later classes. So because of the virtue of interpolation, you're introducing artifacts and noise, which essentially is the equivalent of us adding other frequencies which are close by. So you can sort of think of it as, okay, we had ideally 2 dots, which are like highlighted by the 2 brightest squares in the Fourier transform image, here and here. But the problem is that because we sort of had artifacts, it sort of like spreads out a little bit. It's sort of like blurring it out a little bit. And that's what is essentially happening here. Okay, let's continue doing this. Now we started with this sine wave and we changed the frequency and the angle and stuff. What about something like this? Okay. To give you an example, this is two sine waves, which essentially looks like a grid pattern, like what you would see in a barbed wire or barbed mesh. And so how do you think this would look like? Remember, there are two sine waves here, right? So you will have basically 2 points per one side, and when you reflect it, you get essentially 4 of these, right? And this is fairly simple. In this particular case, it just so happens that perfectly is aligned in a way that you would have very little or very minimal or almost no artifacts, right? Let's continue this further. Now we essentially increase the frequency of this, and as you would see, for each of the dominant frequency we have points, and because it's not perfectly aligned, the values are spread out a little bit, and this is what it would look like. And again, we can keep adding in more and more sine waves as we go along. This was with 4 sine waves, and we can keep adding more and more sine waves and so on, and this becomes pretty complicated, and we are going to get more and more complicated texture and pattern. Again, the more sine waves we add, the less repetition there is going to be because of constructive and destructive interference between these sine waves. So we are actually going to produce more and more unique patterns, as we will see in some seconds. So now let's take our Lena image from before, and if we take the Fourier transform of this, what will happen? You might be thinking that's going to be a lot of frequencies, almost every frequency is going to exist, and you would be absolutely correct. But let's plot it and see what actually we can make out of this, right? If you look at the vertical and the horizontal axis, you will notice that there is a big spike, and that is corresponding to the vertical and the horizontal lines in the image. The image of Lena has a lot of vertical structures like her nose, her shoulder, parts of her hat and hair, and that's what is the vertical spike. And the horizontal spike is a lot of the horizontal structures like the shoulder, the lips, the eyes, the eyebrows, and the values on the feather and so on, right? And you also see a big white bright spot in the center of the image, which means that the frequency is very low, which means that the amount of variation in that sine wave is so low that it's almost like a flat patch, or the color is almost the same, right? It's some uniform color. And that is also correct because her skin tones are pretty smooth. The things on the background are pretty smooth. It's like a fairly single colored, unicolored background, and that's what is represented there. We also see like a diagonal spike, which is indicative of the diagonal line on the hat itself, right? So we can sort of envision what the image would look like, but we will never know how exactly the image is going to be placed. One super important thing to note from this example is that when you go from the left image to the right representation here, what happens is you lose all ordering. What I mean by that is you will never know where that vertical spike is in the image. You will never know where that horizontal spike is in the image, or the diagonal spike. All you know is it does exist with this much quantity, but you do not have any spatiality towards it as you do on the left side spatial domain image. Great. So now let's take the Lena image, let's rotate the image, and I just want you to take a second and think what would happen to the Fourier transform on the right hand side here. If you thought that it would be rotated as well, you are absolutely correct. If you carefully observe, you also notice that the diagonal spikes became much stronger, and that is simply because we introduced more high frequency or like more edgy like components based on the border of the image where it goes from the Lena image to the black structure. Because when we rotated, we didn't want to crop in, we wanted to keep the entire image intact. So we added this black border, but that added artifacts in the Fourier domain. Right? So I have a confession to make. I have been cheating all along. Your Fourier domain does not look like this. It actually looks different. Let me go through each of the lies I've told you by now, and then we will recover how that we got to this point. Lie number 1 is that the real Fourier transform spectrum looks different. It actually looks like this. Let's call the image I. This is the Fourier of image I. So you might be wondering, I don't even see anything here. If you zoom into the video in the center of the Fourier image, you will see like a white sort of dot there, and there are some non-zero values around it, right? But all the other values you don't see. The question is why? Why is this happening? Let's delve deeper into this structure. If you take the maximum value of the Fourier transform of the image, it's going to look something like that, and it's a huge number, right? And the minimum value is very small relatively, right? If you calculate the dynamic range of this, this is about 61 decibels. Recall that the dynamic range of a normal 8-bit image is 24 decibels. And if you have a very fancy DSLR like the Nikon D850, it's something like 42 decibels with 14 bits of information. With 61, almost 61 decibels of dynamic range, this is too hard, right? None of our displays are capable enough to display something like this, right? The question is, we want to increase the dynamic range of our display in an artificial manner, because we know that our displays are not that good, right? That's why you can't see stuff which are like really low value. It will just crush it and make it look like black. So instead, what we will do is we will compress the domain of the function in a non-linear manner so that we can actually see and visualize what is going on. I want you to take a second and think of one common function, mathematical function, which compresses the domain of a function. The answer is the logarithmic function. So what we had done essentially is take the image, and in this particular case we took the log of the Fourier transform, and that's how we could essentially see what is going on. Remember that because it's in log scale, the values which are darker are really small compared to the values which are brighter. The second lie I told you is that I already told you that like Fourier transform is complex, but I was still plotting it, right? The question is, how did I do it? I want you to take a second and think about it. You might be thinking that you were only plotting the real component or the imaginary component, and that's not a bad way. But what essentially I was doing is plotting the magnitude of that signal itself, which takes the square root of the real part, a sum of squares of the square root of the real parts and the imaginary parts, and that's how I got here. Now let's look at the magnitude and phase of the Fourier domain. So this is our image, remember. The magnitude is represented as m, or the absolute value, or the L2 norm, and it's given by just taking the sum of squares of the imaginary part and the real part, which is the x and y parts as I've shown here. Remember that x here represents to the real part and y represents the imaginary part. It's not the xy domain of the spatial domain. Okay. Next, the angle is given by the tan inverse of the imaginary part to the real part, as I've shown here. The magnitude, again, this is the logarithmic magnitude which I'm plotting here, and the phase or the angle looks like this. The angle doesn't really have structure like the magnitude one does. It's a little harder to implement just by looking at it, but it has a beautiful physical significance, as we will see in a second. So let's take this image of Marilyn Monroe, and what we will do is we'll take the Fourier transform of this image, and we will basically just utilize the magnitude, and we will set all the phase values to 0. Essentially, we are throwing out the phase value, and we will take the inverse Fourier transform of that image. I want you to pause the video for a second and think about how that would look like. If you were thinking that you would still see Marilyn, it is very interesting to see that you would see actually nothing at all. There is no order and structure. The magnitude information is not that useful for reconstruction of the image. Now let's flip this around. Let's take the same Fourier transform again. Let's keep the phase values. Let's change the magnitude to the average magnitude value. If we set the magnitude value to 0, nothing will happen. Again, you could have set the phase to 90 degrees here. You would see something similar, but not really much of a change. I want you to think, if you reconstruct this with the phase array intact, but the magnitude set to the average value, what it would look like. If you were thinking that it would still not make any sense because going with what we saw in the center, the answer would be very interesting to see that we actually do see Marilyn's structure of the image pretty well. It almost looks like some filter applied on Marilyn's face. And that's very interesting to see, right? We preserved like the essence of what the Marilyn image is. If I show you the image on the right, you would still say that it looks like a Marilyn image, but it's like weathered or something like that. It's like some filter was added on, but you would still know that it's the same image, right? Which means that phase is actually one of the most important quantities in the Fourier transform and is utilized a lot to compare two images and match two images in something called as phase correlation. And that is going to be a topic of one of the future videos as well, and we will come to that. Phase correlation, it's a beautiful concept. So the last slide I told you is that you take this image on the left, and you ideally would get an image on the right, which you see here, right? This looks very different from the one I was showing you before, where the things were centered. You'll see that there is no center here. You'll be wondering what just happened here. What we were essentially doing is a better visualization trick. This is what you would see when you get the raw output. And there's a trick called the FFT shift, which basically takes the entire image and like flips it, takes all the four corners, pinches it in the center. So almost like that toy we had wherein we fold the paper in the center, right? And that just makes it so that it has more order for us to combine it in a way just to see and visualize it better. In an ideal world, what you would see is like the shift on the without the shift on the left, but for visualization sake, we would basically do the FFT shift so that it's easy for us to interpret. Now let's talk about how we can utilize this Fourier domain to do something cool. Remember that in the previous episode, we talked about how we can do filtering in the spatial domain using convolutions, and we can combine multiple of these guys and to do something really cool. And in this video, I showed you that if you take any spatial filter and you basically take the Fourier domain of that, you can just combine them by just multiplying them instead of full convolution, right? That is even more cooler. So can we have some intuitive understanding of what filtering in the Fourier domain looks like is what we will see now. So, and it's really cool. So let's take this image of Lena on the left. Again, remember that this is the log magnitude spectrum which I'm showing you. But essentially we are performing all these operations in the actual value. This is just for our better visualization, right? Let's say I take this magnitude spectrum, I multiply it with this mask, which is basically this image on the left, right? Which is a circle with like ones in the middle, or 255, and basically black all around. How should the image on the right side look like if I multiply the left image with the Fourier spectrum and then reconstruct it with the output, right? And we are essentially like convolving with this filter in the spatial domain when you take the inverse of this in essence. Remember that the frequency, the lower frequencies are in the center, and as you go higher, like towards like away from the center, you have higher and higher frequencies. And basically on the vertical axis, you have the phase. If you were thinking that the image would be blurry, you were absolutely right. But when we blurred it out, you see these artifacts called ringing, where you have like these halo effects or ghosting effects. That's simply because by the way we are essentially like making this filter, right? This filter has a perfect like sharp cutoff at that frequency, which is non-ideal because like you want it to be smooth, right? Like you want it to be a smoother filter. So in spatial domain, we were doing that smoothing filter, right? And I want you to take a second, pause the video and think about what shape would actually give us something which is smooth without these ringing or like ghosted artifacts. Okay? While we do that, let's go through another example. I've just made the disk smaller. The question is, how will the image look like now? Right? Remember that again, like the lower frequencies are in the center and the higher frequencies are as we go away from the center in the Fourier domain. The question is now, we reduced the number of frequencies we want to preserve, right? With what is white. So essentially you will see a more blurry image. You still see the artifacts, but the artifacts are not as visible as before because everything is more blurry, right? This essentially is called a low pass filter. We can change the shape from a circle to a square or a rectangle, and you would still see a blurry filter, but again the kind of artifacts you would see would be slightly different. Okay, and again this is ringing due to something called as aliasing. Aliasing is a very important concept in the field of computer vision, which you actually see in real life as well, right? The Nyquist criteria for sampling basically tells us that we need to sample at least at double your signal rate to not introduce artifacts, which means that if you have basically some number of pixels in your image and your actual features in the real world are like varying faster than that, you would essentially see these like weird artifacts or these diagonal grating lines which do not exist, right? And this is what is called as moire in the field of photography, and you'll see that over t-shirts with like varying patterns. You'll see that on air conditioners. Anything that is repeating with like very high frequency, it doesn't work, right? So when we introduce something called as an anti-aliasing filter, what happens is this is essentially like an optical low pass filter which blurs your image ever so slightly. And now if you notice, like from the left image to the right image, though the right image is blurred out a little bit, it has lesser artifacts overall. And you know it is blurred out because if you look at the texture on the wall here, it's not as sharp as what is on the left side image. But the grating and all these things which are introducing fake artifacts are much better, right? Great. The question now is, if you bump up the resolution, you can remove the anti-aliasing filter and actually regain the sharpness we had before. Why? Again, the answer is in the Nyquist criteria for sampling. As you're bumping up your sampling rate, you can essentially resolve finer and finer details, and that's the reason why you can do that. So higher resolution sensors in current smartphone cameras or DSLRs or mirrorless cameras do not really have this anti-aliasing filter, right? Some of the pro cameras still do have that because they're lower resolution, because they want to have bigger pixels, as we saw in the previous videos, because having bigger pixels lets you do better low light performance, right? Great. So again, remember that when you add an anti-aliasing filter, you're effectively losing a little bit of resolution because you are blurring the image a little bit. Great. So let's continue filtering the Fourier domain. Now we flipped the mask, which is like we throw out all the things in the smaller low frequency bands in the center and we preserve everything else. I want you to take a second and think about how this would look like. If you were thinking that it would look like the opposite of what it was before, you would be absolutely correct, which is basically it's only preserving the high frequency components. As we see, it is mainly preserving where the brightness and intensity are changing significantly enough, which will essentially be called edges in one of the future videos. And this is what it looks like. And if we reduce the black circle in the middle, which is we're letting in more and more low frequency components, you will essentially see that the edges become more and more bloated, right? Which is kind of sensible. And this is called a high pass filter. Just for you to remember, the image in the high pass would be the original image minus the low pass filtered image. Now remember that we had artifacts and ringing in all those previous scenarios. Let's see how we can make it better. So now if we replace the original low pass filter, which was like a circle or like a square, with something like a Gaussian distribution, which is smooth, what do you think will happen to the image on the right hand side? The image on the right hand side is a beautifully blurred image, and observe that there is no ringing artifacts whatsoever like we saw before. And this is one of the most amazing properties of a Gaussian distribution when you go from spatial to frequency domain, because the Gaussian becomes another Gaussian distribution when you go from spatial to frequency domain or vice versa. And because you preserve the original shape of the structure in both the domains, you essentially will introduce no artifacts, and that's the best thing about the Gaussian distribution. So you can use the Fourier transform to do some noise reduction. Again, if you have a noisy image of Lena like this, and you take the Fourier spectra, you'll also see some amount of noise due to the variations in the values in the Fourier domain. You'll see a lot of high frequency values. You can essentially, if you take the filtered image, this is what it would look like, and you can basically smooth out the image by taking a low pass filter on the Fourier domain, right? And it works very well. So one more thing I wanted to observe is here the high frequency components were like very highlighted, though in the log scale. As we basically reduce the noise, you will see that the spectrum becomes more dim, it becomes nicer and cleaner, and you can essentially go to the Fourier domain and basically scale the high frequency values down in a way to basically reduce the amount of noise, which might be very hard to do in the spatial domain. So this brings me to one of the cool concepts. Remember, we were talking about the Marilyn Monroe image from before, how we could like reconstruct. Let's do something even more cooler. Let's take an image and let's take the Fourier transform and only use the low frequency components. Let's take another image of Einstein in this case, and let's only take the high frequency components. We know how to do both. In the first case, you basically have the white circle in the middle and black all around. In the second image, you basically have the black circle in the middle and white all around, and you reconstruct the image, right? So now you take the low frequency component version here and the high frequency component here, and you take these two images and you literally take element-wise summation in the spatial domain. And this is what it would look like. You might be wondering, okay, what's so cool about this image? Because you're observing this from a very close distance, right? You of course like would probably see Einstein if you're sitting very close to the screen. The farther away you go from the camera, you will start seeing Marilyn Monroe. Another way to do this is if you like close your eyes almost fully and just open a very small sliver, or you would basically press on the side of your eye and like pull it outwards, you will see the Marilyn Monroe image. Pause the video for a second and actually look at it because it's a very, very cool illusion. Awesome. As we keep going forward, we have these things called the Gabor filters, which essentially model how the human brain does process images. Again, if you take the Gabor filter, take it in the frequency domain of the Fourier domain and plot it in the spectra, you will see that it does not cover the entire image space. So it's not really good for reconstruction, but it's good for filtering, like how we built some filters before. One of the most interesting interpretation of the Fourier domain for me has been relating it to the Heisenberg uncertainty principle. The Heisenberg uncertainty principle in physics essentially says that if you have uncertainty in position or space, and you basically have time or frequency uncertainty, they're basically cross-coupled in this way, essentially that if you are very confident about the spatial domain, you're not going to be confident about the frequency domain and vice versa, right? So we can sort of utilize the same ideology here. If there are very slow variations, that means it is low frequency, right? Which means that the same variation happens in a larger scale or space, which means that it's not really perfectly organized in space. We don't know how to locate it in space. This means that it's higher value or closer to the center after FFT shift, which means that in the frequency domain, it's very well localized. It's very well near the center. But in the spatial domain, it could be anywhere on the image and we have no idea what is going on, right? On the other hand, if you have fast spatial variations or high frequency, that means that the same variation happens in a small scale or space, and we can sort of identify where in spatial domain it would be well, right? This means that in the frequency domain, it's higher, the higher value is farther away from the center, and it could be wherever, and even a little bit of noise can move it around, and we don't really know where it is, right? And that's how I interpret the spatial to the frequency domain transformation and vice versa, that if you're confident in the spatial domain, you know exactly where it is. In the frequency domain, it's going to be really spread out. If you're really confident in the frequency domain where it is in the where it is in the frequency domain, it will be really spread out in the spatial domain. And that's how I think about it. Great. So now let's take an image. Let's take the Fourier transform. And now what we can do is, instead of, remember the circular low pass filter example we had before, which is essentially like preserving only a small chunk of the section instead of the full thing, right? And we know the mathematical mapping. If I start increasing the radius of that circle from one like single pixel all the way up to the full image, that is called, and take the inverse Fourier transform, that's called image reconstruction, right? The question is, how many terms do we need for perfect reconstruction? In an ideal world, you'll say, hey, the entire Fourier spectrum, because that's the reality. But the question is, at what point do we visually not see the difference anymore, right? Let's look at that in a second. So the left is showing you the current pattern that's being added for you with the highest frequency component. And on the right hand side, the image is being reconstructed as we keep adding a few terms. Like in about like 3000 terms, we already can make out the perfect image, right? Though the original image has over 100,000 of these terms, with just like a few terms, we can actually like reconstruct the full image. This means that this is one of the amazing ways to compress the image into much smaller number of pixels. Remember, we started this entire video by saying, hey, we want to take an image, we want to break it down into some feature space, where from that feature space, we have a mathematical mapping to get the image back. And this is how the Fourier transform looks like. Remember that we cheated by saying that it's a sum of sines and cosines, and only having some number of sine waves and cosine waves, then as many as the number of pixels, we can fully reconstruct the image itself. And we will do this example in a few more seconds, but let's take a side step and ask the question. Okay, these Fourier transforms are cool, but today I have my neural networks and I'm gonna just have fun with my neural networks. Why do you want to bother with this stuff, right? So one simple way is, a lot of the neural network packages or neural networks implement convolutions as Fourier transforms, especially if you're running this on something like a smartphone where you have a Fourier transform hardware processor, and it might be really useful for us to use that. But let's take another example. Let's say we have our input as X to a neural network, and we want to basically predict the RGB values. Here, X is essentially the location in pixels. You can say like, hey, pixel 0, 0, pixel 10, 10, pixel 100 by 100, right? And what we are trying to do is, for every pixel, there is a color in that image. And we want to make this work only for a single image. Let's not make it too complicated, right? So the question is, if I take an image and I give it enough number of neurons, more neurons than the number of pixels, let's say the image has only 1,000,000 pixels, but I give this 1,000,000,000 neurons. The question is, does this work, right? You have 1,000,000,000 parameters here to make do with. Essentially, you're trying to build a lookup table. The neural network should work, right? Let's have a look, right? The supervision image is on the right, which is what we want to reconstruct. The image on the left is basically different iterations as we continue to train this network, as we'll see in one of the later videos. So even if you train this for like thousands of iterations, you will still see a blurry mess, and it's never going to look like the supervision image on the right side, which is weird, right? We are like, why is this happening? What essentially happens is that even though neural networks are amazing at representing functions, they will always remember the lower frequency components better. So now instead, what we want to do is we want to take this original input and multiply this with something called the sine B, or we call this the embedded Fourier space. We take the positions, we take these positions and basically multiply it by sine waves so that it becomes a higher order polynomial than it actually is. And now we train the same image. Let's look at this. Right? On the left hand side, if you look at it, I'm going to play this again. The standard MLP where we had the previous thing was not good at all. On the right hand side with the Fourier features, it's so much better, right? This is called the positional encoding, and we have a future video coming up on positional encoding, which is one of the most beautiful concepts in modern day computer vision, right? And we can also create these like neural network based spectral losses for neural networks, and these are super useful for something like super resolution, wherein you have like these Samsung or Apple cameras which can do like up to 100 200x, and essentially what you're trying to do is you're saying, I do not really have that many pixels, but I want you to like reconstruct this image so that it looks better than it actually is, right? So you can take an image like the one on the left hand side here, and you can like zoom in beyond what is actually physically possible with the sensor by reconstructing what the image would look like the thing on the right hand side. Using the Fourier transform is great for compressing the images like we saw before, but In reality, we use something called the discrete cosine transform, which is closely related to the Fourier transform, but it only operates on the real domain of the signal. So the biggest advantage is that you maintain lesser data, and it's implementationally cheaper as well to do this, because at the end of the day, all we care about is compression and not really filtering with this stuff. So the discrete cosine transform is given as follows. If you remember the equation from the Fourier transform, it's very similar. Image compression is really good with the Fourier transform, but the problem with Fourier transform is that we have to maintain the real and the imaginary components, and it gets pretty expensive to do that. Instead, we will rely on what is called the discrete cosine transform, which is related to the real part of the fast Fourier transform as we saw before. And the expression looks like this. If you remember it, this is almost just taking the real part of it, and it is more useful for compression than the Fourier domain. And the Fourier domain looks like this. So remember that we started the question with how do we break any image down into known components and what features. In the first case, we were basically using a sum of sine and cosine waves. In the discrete cosine transform, we will be using just two-dimensional cosine waves. And if you're thinking like, hey, does it look like any of the patterns we were seeing before? The answer is absolutely correct. And this is what it would look like. So on the top left corner here, you basically have a cosine transform with zero frequency, which is a flat patch. And as you go towards the right, this is basically cosine waves in the vertical dimension increasing. As you go from top to bottom, it's in the horizontal direction. And as you go like diagonally, it's a sum of these things, right? This essentially, like you can imagine, like we can build up anywhere from like vertical edges to something which look like grid lines, all the way up to something which looks like a full checkerboard, right? These are called the DCT basis functions because this is the basis of how we are going to reconstruct the image. The way you should think about this is take an image, split it up into small patches, and can we represent or approximate each of this patch with something which looks like any of these bases, right? And that's what we are trying to do. And that's how we get the reconstruction. And then if we can do that, we can essentially just save one number which denotes which of these bases we have saved. And when we read it out, we can reconstruct it back. So we take the image of Lena from before, and if we plot the log DCT, this is what it looks like. It's a little different from reading the Fourier transform because there's no imaginary part, so it's only one chunk of that. If you remember the Fourier transform between the FFT shift, that is exactly how this looks like, right? From the top left corner, as you go diagonally outward, the frequency increases. And as you go from the horizontal axis, that's your angle or phase increasing, right? Let's try to compress this. If we don't do anything, we basically have a one-to-one mapping and we exactly have the same number of pixels, right? So what we want to do is we want to zero out some of the pixels on the right-hand side and only save a small amount. So what we will do is just like the Fourier transform, we are going to throw out the pixels at high frequencies. If we do that and we reconstruct the image back, we will see that we see a lot of artifacts like before. The question is, instead of doing this, can we do something much better than that? Whenever we don't know something in computer vision, what we will do is essentially split the image into smaller set of patches, something like 32 by 32 or like 8 by 8. And for each of these patches, we do the same thing like before, which is take the discrete cosine transform. So let's take the discrete cosine transform and then basically let's zoom into the one of these blocks, right? And this is what it will look like. Let's do the same trick we were doing before, which is only maintain a small section. Remember that this is a really small section of the image and then we are approximating it with something in the lower frequency region for that part, right? Now let's do the same thing for each of these blocks and reconstruct it with this newly minted thing. And if you look at the output, it looks pretty decent. It's much better than what we were seeing before, right? You'll see a lot of artifacts on the right hand side. But again, we did an extreme compression in this case. Almost we threw out like 98% of the values. So we are only maintaining 2%, but the image looks much better than that, right? And if I zoom in extremely to this, if you observe very carefully, each of these blocks resemble one of the DCT bases. This is essentially what the JPEG compression or Joint Photographers Expert Group compression does. Again, this is a very extreme case. You probably will never compress this much. Let's look at another realistic example of what JPEG compression would look like, right? So the original image is on the right hand side. If you look at the leftmost image, that's what we were seeing before, but if you zoom out, it looks okay. With more bases preserved, which is like more values non-zero, you will actually see almost like very little compression, right? And this works really, really well. Great. This video has been long. Thanks for sticking with me. With this video, you should be able to understand why we need the frequency domain, what's the key idea of the Fourier transform, how can we filter in the frequency domain, do Fourier features matter in the era of neural networks, and how can we use it, what is the link between the spatial and frequency features. It was an exciting video. See you next time. Bye-bye.